All right, everybody, I hope you enjoyed derivatives of exponential functions, because here is part 2. If part 1 was differentiation, you know what you're in for. Part 2 is integration. Quick recap from our first part was that the derivative of e to the x is e to the x. So written in an integration rule, that implies then that the integral of e to the x with respect to x is likewise e to the x. Here I'm writing it as an indefinite integral, so I'll tag on a constant of integration, and now we have doubled our knowledge, right? So we're going to work a couple integral examples, and then same with the differentiation. I'd love to have you guys practice a bit. Make sure you feel pretty comfortable with these before we call it quits for today. All right, let's dive on in. So we saw in the last video that when we are differentiating e to a power other than x, the chain rule was needed. In the same way, anytime we're integrating e to a power other than x, the opposite, which would be u subbing, is thus needed. So in case it helps, the chain rule is to derivatives as u subbing is to integrals. All right, I'm not sure if that helped or not. But anyways, here's our first example. We're going to try integrating from 0 to 3 the function 1 over 4x dx. So the way this integral is written is typical, but might not be something we're quite used to yet. So I'd like to just start by rewriting to make it a little bit more clear. We really have 1 over e to the 4x with dx off on the side. Sometimes in textbooks you'll see them kick dx to the numerator when the numerator is just 1. But this expanded notation tends to look a little better. I'm going to even go a bit further and just pull that up to the numerator. That's a really good first step. So sometimes just a little bit of rewriting before you even get too far into a u sub is a good idea. So let's consider this now as a u sub. We know that we've got e to a power other than x. So this power here would be our choice of u, because we know how to integrate e to just a simple variable. So let's go ahead and try it. Let's let u be negative 4x. Based off that definition of u and nothing else, the derivative of u is negative 4 with respect to x. Now looking back at our integral real quick, we've just got a dx readily available, so I'll just go ahead and divide both sides of our du equation by negative 4 to give us that perfect match. The other thing that's going on in this problem, something we began talking about together last week, is the limits of integration. We talked through two different methods. Likely you had a preference between the methods, but I'm going to kind of push us the direction of converting the limits, because in the long run it's a really nice technique. So let's see if we can talk through that again together. These original limits of integration, 0 and 3, are for the limits on x, but we're about to convert this integral to be in terms of u. For example, we know next line down we're going to have e to the power of u times negative 1/4 du. So it's technically incorrect to place 0 and 3 like this on the integral, because 0 and 3 are values for x. So let's go ahead and update those to be values for u. I'll do a little work on the side here. Let's take the lower limit of 0. If x is equal to 0, then u, by definition, is negative 4 times that x value, and negative 4 times 0 is actually still 0. So the lower limit is still 0 in terms of u. Now the upper limit was 3 for x. So if x is equal to 3, when we plug that into our definition of u, which says that u is negative 4 times x, we now get a negative 12 for the value of the upper limit. So the new, quote, upper limit is negative 12. The value in converting these limits to u is I will never need to back substitute to the variable x, because this is a definite integral. and that will have its advantages. So let's just keep rolling with it that way. If it's not your preference, we can of course talk about the other option next class for sure. So let's see if we can go ahead and keep going with our integral from here. So I'm going to kick this negative 1/4 out front and just rewrite it one more time in one color just so we can take a step to integrate. So when we integrate e to the u, we just get back e to the u. And this is a definite integral, so now we'll spend some time evaluating from 0 to negative 12. Notice again the value is we never have to go back to x. Ooh, that's a weird looking, I don't know what I did there, sorry. This should just be e to the u. So we're going to plug in 0 and negative 12 because those are u values and not x values. Great, so I'm just going to go ahead and show plugging in negative 12 for the value of u for the upper limit, and then subtracting off 0 as the lower limit. You'll notice this time around I just went ahead and pulled the negative 1/4 out front. We know it would be applied to both terms, so sometimes people do that just to save a little bit of space or time. So I'll go ahead and do that here too. And looks like we're pretty close. We're basically done. We've stuck in the numbers, but looks like we could simplify a bit more. For example, we know that e to the power of 0 is just 1. And that should be good enough right there. If you want to distribute the negative 1/4 to both terms, you can. But this would be the numerical value for the original definite integral. So of course, anytime we have a definite integral, it takes a little bit more work, I would say, than an indefinite integral. So hopefully that process feels pretty good. In some of the homework that'll come up later, you may choose to make an observation, which maybe I'll address real quick here before we move on to the next example. And that is, there are certain derivatives and integrals you see enough that you develop an eye for the pattern. For example, we're going to be integrating e to a number times x very often. It just happened in this example. It's going to come up in the homework. So I'm letting k hold the place of any constant. Let me show you through a u sub how we can generalize this result. So if we let u equal k times x, right, whatever k stands for, in our last example the k value I think was negative 4. Based off that definition, the derivative would just be k with respect to x. And I'm not going to have that k typically within the problem, so I divide by it to start getting a perfect match. So this is kind of a little mini proof that you can take for granted moving forward. When I then rewrite my integral, I'm going to have e to the u times 1 over k du. And if I'd like, I can pull out the 1 over k, because k is just a constant. And we know that the integral of e to the u is just e to the u. So we get back 1 over k e to the u plus the constant of integration. And then if I go ahead and just back substitute, we know that u is holding the place of kx. Alright, this result by itself maybe doesn't seem super useful, but it's actually really helpful, and maybe I'll write it in a slightly different form. I'm going to write it e to the kx over k. I think you guys will agree this is equivalent plus c. So this means anytime we're integrating e to a number times x, this pattern will always hold true. So I leave it up to you whether you choose to do a u sub every time or you use this as a pattern and you take this result for granted. It doesn't really matter in the long run which of those you do, but it is something that we'll see perhaps frequently enough that it's worth staring at together. So let me just give one short example of this if I can get my screen to move. I'll just sneak it in right here. I wasn't going to take too much time, but for example, e to the 2x, we can now say this is just e to the 2x over 2 plus c if it's integrated, because the 2 is like the k in this formula here. So anyways, take it or leave it. It's just kind of a cool little shortcut. I hope you enjoy that. It might mean more to us as we practice more. So let's go ahead and do some more just standard kind of u sub examples. The second example has e to the power of sine x times cosine of x dx. And of course, we just practiced with u sub last week, so we're still kind of developing some strategies for identifying which piece is u and then which piece is du. But so far, it seems intuitive that u would be the exponent on e, because we do know that e to a simple variable integrates to just e to that simple variable. So it'd be nice if we could take out sine of x and replace it with simply u. So let's try that. Based off this definition of u and nothing else, the derivative of sine is cosine, taken with respect to x. Looking back at my integral, I happily see it's everything that I wanted it to be. So we do have actually a pretty good match, if you will, for this u sub example. That means when we rewrite the integral in terms of u, we have simply e to the u du, and that's looking very nice. We know the integral of e to the u, again, is just e to the u. Tag on your constant of integration, and since this is indefinite, we do need to back sub to return to the original variable. So anytime we see a u, let's pop in our sine of x, and this will be it. So e to the power of sine x plus c. And I haven't said this yet in this video, but just remember, anytime you integrate, you can take the result, in this case e to the sine of x plus c. Differentiating this result must give back the original. So if I think through this quickly, the derivative of e to the sine of x would be itself e to the sine of x times the derivative of the power, which would be times cosine. The derivative of the c here would be 0. So what we just said out loud sounds a whole lot like what we started with, which was e to the sine of x times cosine of x. So anytime you have integration, of course, you can check your work by differentiating the result and making sure it matches what you started with. All right, I've got just one more for you. Let's go ahead and give it a try. Don't be alarmed, but now we are being tasked with integrating e to the square root of x divided by the square root of x. This one looks, I would say, messier than our last example. So I'm going to give myself a couple steps just to process the integral and to rewrite it in hopes that I can identify a good choice of u. Right now you might have some guesses. Those guesses are probably good guesses. I'm just going to reinforce that sometimes rewriting the integral will help you see u. Help y-o-u see u, the variable u. All right. Well, we know a radical is the same as a 1/2 power. So e to the square root of x is really e to the x to the 1/2. Dividing by a square root is the same as dividing by x to the 1/2. I don't really like the fraction feel to this problem, so I'm going to try pulling up the denominator. So I'm going to have e to the x to the 1/2 times, and then when I bring the x up, it's going to come up as x to the negative 1/2 when we bring it from the denominator up to the numerator. So this x to the 1/2 swings upstairs as x to the negative 1/2. And now I'm seeing a little stronger relationship between a possible u and du. I'm noticing that this exponent on e, which is x to the 1/2, differentiates to feel very similar to x to the negative 1/2, because we know that a half minus 1 would be negative 1/2. So the rewrite is up to you, but if you're having a hard time determining u, it may help to rewrite. So let's go ahead and try this. Let's go ahead and try letting u be x to the power of 1/2. We know the derivative of x to the power of 1/2 would be 1/2 x to the negative 1/2 with respect to x. And that looks very similar to what we had over here, but we're off by that factor of 1/2. So I'm going to simply times both sides of this equation by 2 to get 2 du is now the same as x to the negative 1/2 dx. So if we go ahead and rewrite the integral in terms of u's and du's, looks like we should have e to this just the power of u now. And all my red underlined stuff gets swapped out with a 2 du. So let's see. If you'd like, you can pull that 2 out front of the integral. It's always fair to pull a constant out front if it makes it feel a little bit more simple. We know now that the integral of e to the u is just e to the u. It's indefinite, so we tag on our plus c. And this one's wrapping up rather quickly despite the slow start. So if we go ahead and back substitute, u becomes x to the 1/2 based on our original definition of u, and we still keep that constant of integration. So 2e raised to the x to the 1/2 plus c. Because this one started off with radical notation, it wouldn't be too strange to end with radical notation, so maybe I'll end with 2e to the square root of x plus c. And that would then be the final antiderivative for the original problem. I'll leave it to you on this one to verify that differentiating this result will in fact yield the first line we started with, the actual integrand that we started with. So I hope that gives you a little interest and explanation on integrating with e to the x. As you can see, it dovetails nicely with the u-subbing technique we began learning last week, and that we'll see used in integration really from here on forward. So if these examples are making a little bit of sense, we can move on to practice. If they're not, go ahead and just talk through them a bit together until everybody feels pretty clear. And when you are ready, I have the same directions as the last video, which are when I'm done explaining, you can pause this video. On the whiteboards, feel free to now try out homework 3B problems 8 through 12. 1 through 7 were derivatives, 8 through 12 now are integrals. Try them on the whiteboards with each other, discuss them and take some photos of your work. And once you feel ready, you can then play this video to check your solutions on the boards. Remember that your process could look a little different than mine, so just make sure our end solutions are looking about the same. And again, pictures of your work will help me just be able to see how you guys work through them. So pause the video. The other thing you may need to do at this point in time is take a break. If I've done my math correctly, it's probably time for a break. So maybe you can pause the video, give yourselves 15 minutes to take a mental break, and then when you come back, try them on the boards, and then play the video. Okay, you tried them, right? Got them all done? Well then, let's compare. So we did have 2 definite integrals in the homework, and I know my strategy may be a little different from yours, but I am converting my limits of integration like I did in the example on this video. So I have a final answer here that looks like negative 1 over pi e to the negative 2 pi plus 1 over pi. If you have something that's equivalent to this, that's a good thing. I'll let you guys pause and see if you need to double check any of the steps on this definite integral. Okay, let's take a peek at number 9. This one was a much more straightforward problem because we are back to indefinite, and the u sub worked out pretty well. So this quantity under the radical, 1 plus e to the x, was u. The derivative was basically everything else. So it actually was a pretty nice u sub the radical got rewritten as a 1/2 power, and then we utilized the power rule. So we added 1 divided by that new power. Indefinite, so we tagged on a plus c. Anytime it's indefinite, we back sub to the original variable. So final answer could be expressed as 2/3 times the quantity 1 plus e to the x raised to the 3/2 plus your constant of integration. Number 10, this one you could work it a couple different ways. The strategy I chose to use was I went ahead and expanded the quantity twice, and then I FOILed. So e to the x times e to the x was e to the 2x. E to the x times e to the negative x makes e to the 0. E to the negative x times e to the x is another e to the 0, because again, negative x plus x is just 0. And then e to the negative x times e to the negative x, adding those powers gives us e to the negative 2x. E to the 0 is just 1. So when I combined those two middle terms, I got 2. And then I went ahead and utilized the small proof that we had done earlier. So anytime I'm integrating e to a constant times x, I made use of the fact that it'll just be e to the constant times x divided by the constant. You may have done u subs, and that's completely fine as well. So just to clarify, when I integrated e to the 2x, I just got e to the 2x over 2 from this nice handy-dandy rule on the side. The integral of 2, of course, is just 2x. It just gains the variable. Careful not to say 0, because that would be the derivative. And then the integral of e to the negative 2x would be e to the negative 2x over negative 2. Still indefinite, so we tag on that plus c, and we should be good to go. So your work may have easily been done a little different than mine. Problem number 11, I like this one a lot. It's rather straightforward, but it gets some trig in there. You can use u as tangent, because tangent is the exponent on e, and tangent differentiates to the other piece of the integral, which is that secant squared of x. So this one worked pretty nicely. The last one I think in the homework was number 12. This was similar to the last example I did on the video, because rewriting it first probably would be beneficial. E to the 1 over x squared, as it's written, is a little complicated. So I started by rewriting 1 over x as x to the negative 1, and then the 1 over x squared on the bottom comes up as x to the negative 2. So this x squared, if you move it up, would become x to the negative 2. Then it helps you see the relationship between x to the negative 1 as a u term, and then x to the negative 2 tied into the derivative of that u term. I converted the limits of integration, like what we talked about. So I got a lower limit of 1 and an upper limit of 1/2. And in the end, I went ahead and stated my final answer as e minus e to the 1/2. Of course, the order could have been negative e to the 1/2 plus e, or maybe you guys wrote it as e minus the square root of x. That would work too. And that was definite, so keep doing weird things, sorry. E minus e square root of e. Ooh. All right, there we go. So this one was definite, and that's why the end result does not have a plus c. Remember, e is just a number, so even though it doesn't feel like it, these are just numbers at the end. They would be irrational values. So I hope you guys have done pretty well with these problems. That's a wrap to the homework for today. So we'll have one more video with another topic, and then we'll close out for today. So on to the next video.